During the course of any organic reaction, the structure of molecule is altered. And during this alteration of structure, one or more chiral centers may be created. And we saw these kind of reaction in this chapter also. Starting from an alkene, which is achiral, we synthesize new organic molecules with the chiral centers. So whenever in a chemical reaction one or more chiral centers are created, then we have to ask a question. Do we get only one enantiomer as a product, or do we get a racemic mixture? And if we get a more than one chiral center, will the product be a meso compound or will it be a diastereomer? And uh, if we get multiple chiral centers, then how many stereoisomers are possible? As we will see in a little while later, that the stereochemistry or product for some of these reactions depend on the stereochemistry of our starting material, which is alkene. So therefore, some of these reactions are called stereospecific. Stereospecific reaction means that if we start with a certain stereochemistry of a starting material, we will get only certain specific stereoisomer as a product. So those kind of reactions are known as stereospecific. Let's try to understand the stereochemistry of a reaction product when we start with a reactant which is achiral and the product does have chiral centers. For example, we saw that the reaction of bromine with 2-butene gives us a 2,3-dibromobutane. So let's write the reaction. The product is the starting material, that is 2-butene, is achiral. However, in the product, we have two chiral centers, and these chiral centers are shown here. And if you recall the information from stereochemistry, any molecule which has n chiral centers, the number of stereoisomers possible can be calculated by the formula 2 to the n. So technically, this product may have 2 to the n stereo possibilities. So it means 2 to the 2, which is 4 stereoisomers are possible for this product. So it means 2,3-dibromobutane can have 4 stereoisomers. However, if we analyze this molecule closely, we see that there is a plane of symmetry. So that means two of those stereoisomers are meso compounds. So therefore, the possible outcomes, possible stereoisomers, is a pair of enantiomer and a meso compound. Okay, so those are the possible stereoisomers for this compound. But I'm not saying that all will be formed during this reaction. Now, because if all of them are formed in the reaction, then that reaction will be non-stereospecific. But if only a selective stereoisomer is formed, then the reaction is stereospecific. Okay, so we will see in reaction mechanism what stereoisomers are formed. Do we have all stereoisomers which will be formed in this reaction, or a specific one? That we will figure out in next slide. But for now, just remember that without even looking at the mechanism, the overall combinations which are possible are 3. Now our starting material, although it does not have any chiral center, but our starting material can have two stereo uh, possibilities. It can be either cis-2-butene or it can be trans-2-butene. And the final product have three stereoisomer possibilities, as I mentioned, a pair of enantiomer and a meso compound. Now the question is, if we start with the cis alkene in the beginning, what will be the stereochemistry of the product? And if we start with the trans alkene, then what will be the stereo outcome? Do we get same stereo outcome regardless of the cis or trans alkene starting material? We don't know. So all those answers can be obtained by looking at the mechanism of the reaction. And if starting with a specific stereoisomer we get a specific stereo product, then the reaction is known as stereospecific. But if we get all stereoisomers, regardless of what stereochemistry is started in the alkene, then the reaction will be non-stereospecific. So let's take a look at the mechanism. As you may recall, that the mechanism of halogenation involves a cyclic three-membered bridge intermediate. We call it brominium intermediate. So if we start with cis-2-butene, so our starting alkene is cis, we will get two possibilities of the bridging intermediate. Either the bridge will form on top, so that means that the bromine attacks from the top. That's one possibility. So this possibility will lead to this intermediate. The second possibility is that the attack happens from the bottom, and so therefore the bridge will be formed at the bottom. So this bottom attack will give rise to this intermediate. So it means if we start with cis-2-butene, there are two stereochemical outcomes. Either the bridge will be on the top side or on the bottom side. Now, if you see these bridged intermediates, you will see that there is a plane of symmetry in both of them. Okay. Because there is a plane of symmetry, so both of these, although they do have a chiral center, they are achiral. So therefore, these two are meso compounds. So our bridge is a meso compound. So technically, both of these are same, and they are meso compound. So our bridging intermediate, regardless of the mode of attack, whether the attack is from the top side or the bottom side, both intermediates are identical. So at this step, there is no specificity. If we start with this cis-2-butene, let's see what happens in the next step. So as we learned that both brominium intermediate are identical, so we only need to start with one. The other one will give the same products. So now the next step in this mechanism is the attack of a bromide nucleophile from the anti-position. So that means the other side of the bridge to the carbon atom. Now there are two base carbon atoms. Either the attack may happen at carbon number 2 or the attack may happen at carbon number 3. Both of these attacks have equal probabilities. So that means 50% chance is that the attack may happen to carbon number 2, and the other 50% chance is that the attack may happen at carbon number 3. So let's take a look at what happens if the attack takes place at carbon number 3 first. So if this bromine or bromide nucleophile attacks at carbon 3, and then that will mean that the bridge will break from this side and the bond will move to bromine, and we will get this product. Okay, so in this product, the original bridging bromide ion is on top. The number 2 bromide, which attacked from the bottom, is present here. And now this compound has 2 stereo centers, one here and one here. Right? And if you calculate the stereochemistry of this compound, you will find that both number, so this is 1, 2, 3, and 4. So at number 2 is the R configuration, and number 3 is also R. So therefore this compound is 2R, 3R, 2,3 dibromo butane. So that means if the bromide nucleophile attacks at number 3, we get this stereoisomer. Now let's see what happens if the bromide attacks at number 2 carbon. So if bromide attacks at number 2 carbon, so this new nucleophile, so let me remove the green ones now, and the bond will move here. In this case, the product will be that original bridged bromide ion will be present at carbon number 3. So that's the original bromide which was present in the bridge, and the new nucleophile is present down here because the attack is at anti-position. So in this case, if you calculate the stereochemistry of this molecule, this one also has 2 stereo centers. Now at number 2 we have S configuration, and at number 3 we also have S configuration. So therefore this molecule is 2S, 3S, 2,3 dibromo butane. So that means that if the attack takes place at number 3 position, we get R configuration, and if attack takes place at number 2 position, then we get S configuration, and both of these are mirror images of each other. Now 50% chance is that we're gonna get R, and 50% chance is that we're gonna get S. So therefore product will be a racemic mixture. Racemic mixture, we know that is 50-50 mixture of R plus S. So therefore, if we conduct the bromination of cis-2-butene, we will get a racemic mixture of R and S enantiomers. We'll get both enantiomers, but they will be a racemic mixture. So the quantity of R and S will be 50-50. Now let's investigate the stereochemistry of product if we start with trans-2-butene. Just like before, the initial attack of nucleophile on bromine can take place from the top side, or it can also take place from the bottom side. So if the attack happens, initial nucleophilic attack happens from the top side, then the brominium ion intermediate will form, the ring will form on the top side. So this will be the brominium ion intermediate. Now on the other hand, if the initial attack happens from the bottom side, in that case the brominium intermediate will have a cyclic 3-membered ring structure at the bottom. So this attack will give rise to this intermediate. So it means in the initial attack there are 2 possible brominium ion intermediates. Interestingly, in this case there is no plane of symmetry. So there is no plane of symmetry. So therefore these 2 compounds are unique species. So they are not mirror images, so they are not mesocompound. In fact, these two compounds are mirror images of each other. So therefore, both of these are pair of enantiomers. They are mirror images of each other. So now in next step, we know that bromide ion will act as a nucleophile, and it will attack at the anti-position. So now we have two brominium ion intermediates, and we will see what happens when in the step number 2 anti-position attack by bromide nucleophile takes place. In step number 2, the bromide nucleophile will attack the brominium bridged intermediate at the anti position, which is on the other side of the bridge. So I'm gonna take the example of the brominium ion intermediate where the bridge is on the top. So again, there are two possible carbon sites where the bromide nucleophile can attack. It can attack either at number 2 position, or it may attack at number 3 position. So let's first take a look at what happens when the bromide nucleophile attacks at number 3 position. In this attack, a new bond between number 3 carbon and the bromide ion will be formed, and the bond between carbon and bridging bromide will break, and the electrons will move to the bromide. So in this reaction, we will see a product in which the original bridged bromide is present on the top, and the new bromide nucleophile is present at the bottom. Now, this compound has a plane of symmetry. It is not visible as such here, but because the plane of symmetry is diagonally, so there's a diagonal plane of symmetry. So so as you can see, everything, so that's a diagonal plane of symmetry. If you draw this molecule in 3 dimension, you will see that there is a plane of symmetry. Although there are two chiral centers, so this is a new chiral center and this is also a chiral center, but there is a plane of symmetry. Therefore, this compound is a meso compound. Now, if the bromide nucleophile attacks at number 2 carbon, in that case, the product will be generated in such a way that the bridging bromide will be on the number 3 carbon, and the new nucleophile bromide is present here. In this case, again, there is a plane of symmetry present. So this is also a meso compound, and it is evident they are meso compound because when you draw the stereochemistry configuration of these molecules, you will see both the stereochemistry configuration is exactly opposite to each other. Okay, so although their stereochemistry configuration is there, but because there is a plane of symmetry, so they are meso compound, and therefore they are identical. Okay. So it means that if we start with a trans-2-butene, the bromination of trans-2-butene will result in a meso compound. So given these results, we can say that addition of halogens to an alkene is stereospecific. So starting from a cis alkene, we always get a pair of enantiomers, and it will be a racemic mixture at the end. But if we conduct halogenation of trans alkene, we will get a meso compound as our product. So we can define stereospecific reaction as a reaction in which the stereochemistry of the product depends on the stereochemistry of the starting material. In the previous example, which we just saw, that is the halogenation of 2-butene, we noticed that starting from achiral alkene, we can get chiral products at the end. The addition of halogens to alkene takes place at antiposition, that is, halogens are added on the opposite side of the carbon-carbon double bond. Now let's take a look at another addition reaction in which the addition takes place at syn position, that is, addition of atoms or groups takes place on the same side of the carbon-carbon double bond. So this reaction is oxidation of 2-butene with transition metal oxide, that is osmium tetroxide. We know that if we start with an alkene such as 2-butene and we treat this 2-butene with osmium tetroxide in presence of a hydrogen peroxide, the end product is a glycol. And this addition takes place at syn side, that is, the OH groups are present on the same side. Again, in this reaction, our starting material is achiral, but our end product does have 2 chiral centers. So therefore, our product have multiple stereo isomer possibilities. We know that it's gonna be 2 to the n, but again, because there is a plane of symmetry present, so it is possible that one will be the pair of enantiomer and other stereochemical outcome will be a mesocompound. So let's take an example where the oxidation takes place on cis-2-butene. We know that in the first step of this oxidation reaction, there is a formation of a cyclic osmate intermediate, and then cyclic osmate intermediate breaks down by reaction of water to give a glycol. So if we start with this cis-2-butene, the cyclic osmate may form on the top side. So that's one possibility, or it may also form at the bottom side. So it means the intermediate have 2 possibilities. Either it may be on top side or at the bottom side. If the cyclic intermediate forms at the bottom side, then subsequent decay of the cyclic intermediate will result in this product. And if the cyclic osmate forms on the top side, then the subsequent decay of that osmate to result in a diol will give us this product. Okay, so now as we understand that there are 2 possibilities of products, let's compare those products. If we look at these products, we will notice that there is a plane of symmetry in both of them. So therefore, these products are mesocompounds and they are identical. So what we can see here is that if we start from cis-2-butene, we will get a meso 2,3-butane diol. Applying the same concept in case of trans-2-butene, we will notice that in this case there is no plane of symmetry and the 2 outcomes are mirror images of each other. So therefore in this case we get a pair of enantiomers which are a racemic mixture. So 50% one isomer and another 50% the other isomer. So to conclude, we can say that any oxidation of cis-2-butene gives us a mesocompound, and oxidation of trans-2-butene give us a pair of enantiomers which are racemic mixture. So therefore this reaction is also stereospecific, because starting with a specific stereoisomer, whether it's a cis or trans, we end up getting a specific stereoisomer. So therefore this reaction is also a stereospecific reaction. So we have seen two examples in which we started with the achiral compound and the products had a chiral center. So we saw halogenation reaction. In halogenation, our alkene was achiral and the end product was either a mixture of enantiomers, so both were chiral, or a meso compound. So meso compound also has a chiral center. In the second example, we saw the oxidation of alkenes by osmium tetroxide. In that case also we started with achiral alkene and we end up with either a chiral pair of enantiomers or a meso compound. So both enantiomers also had chiral center and meso compound also had chiral center. However, there is an important distinction. We know that meso compounds, although they have chiral centers, they are optically inactive. Okay, and a racemic mixture of R and S, is also optically inactive. Okay, so this illustrates a very important point about creation of chiral molecules. So that point is that if we start with a achiral compound, our product will always be optically inactive. We may get a chiral centers, but it will be optically inactive. So therefore we can say that optically active products can never be produced from achiral starting material. Now I would like to point out here is that racemic mixture is optically inactive because it's 50-50. Optically active means only one enantiomer. Okay, so any of those stereospecific reactions we saw earlier did not give us single pure enantiomer. They either gave us a mixture of enantiomers or a meso compound. So in both cases, the product was optically inactive. So we can say although the molecules of the product may be chiral, the product is always optically inactive. So remember this point, that we can never get a pure optically active molecule if we start with achiral starting material or achiral reagent. So now let us consider a reaction in which our starting alkene is chiral. So as you can see that this molecule is chiral, so there is a chiral center. So chiral means it may have a chiral center anywhere within the molecule. It doesn't have to be on the double bond, because that's never going to happen. As long as there is a chiral center anywhere in the molecule, then our starting material is chiral. So if we conduct the bromination reaction on this chiral alkene, again the addition will be anti-addition, so one bromine will be on top, the other one at bottom. And if you draw the cyclic chair structure, you will see that we get a only one enantiomer at the end. Only a single diastereomer is formed. And the why only a single diastereomer? Because of the presence of this bulky tertiary alkyl group. This chair will not flip into the other compound where bromides are on equatorial, because the bulky tertiary alkyl group does not want to be in the axial position, so the chair flip to give the other enantiomer is not possible. So only single diastereomer is present at the end. So because we have only single diastereomer at the end, so our product is optically active. So that confirms the point which we illustrated in previous slide, that if you start with a chiral material, the end product will always be optically active. In last few decades, scientists have discovered a method to synthesize optically active product from a achiral starting material. So this is quite opposite to what we just uh, stated in previous two slides. So we stated that achiral starting material can never produce an optically active product. But this is a new technique. So in this technique, the reaction is carried out in such a way that the environment in which the reaction is done is chiral. So what's the meaning of chiral environment? The meaning of chiral environment is that maybe the solvent in which the reaction is carried out is chiral, or a catalyst which is used during the reaction is a chiral or optically active. So in that case, if our starting material is achiral, but our catalyst or the solvent is optically active, then the product will also be optically pure, or only one enantiomer will form rather than forming a meso compound or a racemic mixture. So these kind of reactions are known as enantioselective reactions. So enantioselective reaction means that only one enantiomer is selected to be synthesized in these reactions. So one of the catalysts which is used for this technique is called BINAP, which stands for 2,2-bis diphenyl phosphenyl 1,1' binaptyl, and the structure of this catalyst is shown here. Now, because of bulky triphenylphosphine and these naphthyl rings, the rotation around this single bond is prohibited. So therefore, this large molecule exists either as a S or a levorotatory compound or a dextrorotatory. So it has two enantiomers, and they are mirror images of each other. Treating the R isomer of BINAP with ruthenium-3 chloride forms a complex in which ruthenium is bound in the chiral environment of the large BINAP molecule. So this large complex molecule is soluble in dichloromethane, and it is used as a catalyst for hydrogenation of any alkene. Earlier we studied the metal hydrogenation of alkene, in which the hydrogen is added to alkene in presence of a transition metal such as nickel or platinum. That kind of technique is known as heterogeneous catalysis because metal is present as a solid, and our alkenes and hydrogens are present as liquid or gas phases. So they are in different phases. That's why it's known as heterogeneous catalysis. In this kind of hydrogenation, the entire catalyst as well as our alkene and hydrogen, they are all dissolved in a same solvent, which is dichloromethane. So therefore this kind of hydrogenation is known as homogeneous hydrogenation reaction. So using the chiral catalyst, which is the complex between ruthenium and R-BNAP, we get only one enantiomer as a product, and this catalyst is employed in production of the pain-killing medicine naproxen. Only the S stereoisomer of naproxen is active, or only so it means that only the S naproxen has the pain relieving properties. So therefore the technique of homogeneous catalysis using this chiral catalyst is employed so that our product is pure in one enantiomer. Although it's still not 100% pure, there is some likelihood of R enantiomer which will also be generated, but as you can see from the enantiomeric access calculation, it is pretty close to 100%. So therefore we can conclude that if you want to produce an optically pure compound from a chiral starting material, the reaction must be carried out in a chiral environment. The binary ruthenium complexes are somewhat specific for what kind of double bond they can reduce. The double bond must have some kind of neighboring group that serves as a directing group. For example, in this molecule you can see that we have two carbon-carbon double bond, but when we do the hydrogenation, only the bond where neighboring OH group is present, only this bond gets reduced. So as you can see, hydrogen gets added only to this bond and nothing happens to the other bond. Starting with the S binap complex, we get R stereoisomer, and if we use the R complex, then we get the S stereoisomer. But the main point here is that this catalyst will hydrolyze only those carbon-carbon double bond who have a neighboring functional group. On the other hand, if you conduct the hydrogenation in presence of a metal catalyst such as platinum or nickel, that hydrogenation will reduce all carbon-carbon double bonds. So in this case, all double bonds will be reduced. So in metal catalyzed hydrogenation, there is no specificity. It will hydrolyze all carbon-carbon double bonds. With that, we conclude chapter number 6. This chapter is one of the most important chapter in organic chemistry. In this chapter, we learned how to draw a reaction mechanism. We also learned how to recognize patterns in a reaction mechanism. Then we discussed about electrophilic addition reactions, and we learned mechanisms of various electrophilic addition reactions of alkenes. And we also discussed the oxidation and reduction, and finally we learned what are stereospecific reactions and how to predict the stereospecificity of the product if our starting alkene is a cis or a trans alkene. Thank you everyone for watching the lecture. If you have any question, let me know. Have a wonderful rest of the day. Bye bye.